Hello everyone, welcome to Engineering Explained channel. In this session, I am going to take Basic Thermodynamics Model 2, Lecture 1, that is the first law of thermodynamics. In that, I am going to take the first part, that is the Joules experiments. For the Joules experiments, here we are going to take into consideration how the experiment setup is there and how the experiment is conducted that we will take here. Let us consider a closed system. This is a closed system consists of known mass of water contained in an adiabatic vessel. Okay, this is known mass of water is contained in the adiabatic vessel. That means there is no heat transfer through this wall. Having a thermometer and a paddle wheel as shown in figure 4.1. The thermometer and a paddle wheel. Okay, that is a stirring wheel. Let a certain amount of work W12 to be done upon the system by the pedal wheel. Okay, here by the pedal wheel, when it stirs, the particular amount of work is done. That is a stirring work we are going to call. Okay, or a pedal wheel work. The pedal wheel work is done on the system. Okay, the closed fluid is the system. On the system, W1 to 2 amount of work is done. And the quantity of work done can be measured by the fall of heat. What quantity of work is applied, that is measured by this fall of heat. That means work is equal to force into distance. Okay, the force is what amount of weight is there. This weight is the force and the distance for which the weight is falling. Okay, that is gives the work how much quantity of work done on the system, which drives the pedal wheel through a pulley. Okay, that whatever the weight is there, which drives the pedal wheel through this pulley. Then that work done is represented by the on the xy coordinates 1 to 2 as a W1 to 2. And when if you remove this insulation, the diabetic walls, then the initially the temperature is T1. After the pedal wheel work, the temperature is increased to T2. Then the when we remove this insulation from the higher temperature to the lower temperature, heat will be transferring, and that is represented as the Q2 to 1. And that discussion will take in the next slide. The system was initially at a temperature of T1, the same as that of the atmosphere, and after the work transfer, the temperature rise to T2. Due to the work transfer, the temperature increases to the T2. The pressure is always 1 atmosphere. The process 1 to 2 undergoes by the system is shown in figure 4.2. Okay, the 1 to 2 what is there in the figure 4.2 we have taken in the xy curve is generalized thermodynamics coordinates xy. Let the insulation now be removed. The system and the surroundings interact by heat transfer till the system returns to the original temperature of T. The till the temperature of the system reaches to the original temperature T1, heat transfer is taking place, then attaining the condition of thermal equilibrium with the atmosphere. The thermal equilibrium is attained. Both the atmosphere and this system has the same temperature. That is the thermal equilibrium. The amount of heat transfer Q2 to 1 from the system to during this process 2 to 1 is shown in figure 4.2. In the previous slide, we have taken that Q2 to 1, which is shown again on the curve Q2 to 1 can be estimated. That Q2 to 1 also we can estimate by taking the temperature difference. Okay, if we have the temperature difference, the heat transfer we can find out from it. The system is thus executes a cycle 1 to 2 and 2 to 1. Then thus there is a complete cycle. Therefore, the system executes a cycle which consists of definite amount of work input W1 to 2 to the system and followed by the heat transfer of an amount of heat Q2 to 1 from the system. Now, it has been found that this W1 to 2 is always proportional to the heat Q2 to 1. Okay, W1 to 2 is always proportional to the heat Q2 to 1. And the constant of proportionality is called as Joule's equivalent or the mechanical equivalent of heat. Okay, the proportional these two, the proportional constant if you take, there is a J, that is a Joule's equivalent of heat or a mechanical equivalent of heat. In this simple example given here, there are only two energy transfer quantities as shown as the system performs a thermodynamic system. What example we have taken? There is a only two quantities. One is work transfer to the system, another one is heat transfer from the system. If the cycle involves many more heat and work quantities, the same result will be found. The same result. The heat transfer is proportional to the work transfer. Then that is expressed algebraically if the number of heat transfer, number of work transfer are the summation of work for the cycle is proportional to the summation of heat for the cycle, and for that the Joule's equivalent of heat or a Joule's constant is taken as the proportionality constant. The same can be written as where Joule is the Joule's equivalent. This is also expressed in the form cyclic integral of dW is equal to J into cyclic integral of the dQ, as both work and heat of integral form as a path functions, and that's why we can take the number of works. The cyclic integral of dW is equal to J into cyclic integral of dQ, where the symbol J denotes the cyclic integral for the closed path. This the whatever this symbol is denotes that cyclic integral for the closed path. This whatever this equation is there, this is the first law for the closed system undergoing cycle. Both the equations are the used for the first law for the closed system undergoing a cycle. It is accepted as a general law of nature since no violation of it has ever been demonstrated. Never been, there is no violation is demonstrated till now. In the SI system of units, both heat and work are measured in the derived unit of energy, the joule. The constant of proportionality J is therefore J equal to 1 Newton meter per Kelvin. And this is the Joule's experiment. By that we are going to get these relations, okay, which is the first law of thermodynamics undergoing a cycle. Okay, this is the first law of thermodynamics Joule's experiment. In the further session, I am going to take the first law of thermodynamics applied for the closed system for the cyclic process, and first law of thermodynamics for the closed system undergoing a change of state or a non-cyclic process. Okay, thanks for watching. If you like, share, subscribe, and comment.